What I want to do here is recap what we understand about the fundamental forces. If you have followed along with this video series, then we have definitely talked about two fundamental forces, gravity and electricity. So I want to recap these and start to build up on them. So gravity, reminder, the gravitational force just says if there are two objects of mass, we have M1, M2. Doesn't matter what they are. It could be a planet and the moon. It could be you and me. Doesn't matter. There's always this attractive gravitational force between those objects. And it goes as Newton's gravitational constant, big G, mass of one body, mass of second body, divided by the distance. All right? There's your radius squared. The distance between them. And that's our gravitational force. Once again, always, always, always attractive. Then we can switch to this electric force. And this is a property of objects that have charge. Every atom will have some mass and some charge with it. Proton will have a net positive charge, electron net negative. So the electric force goes as the electric force is K, this Coulomb's constant. Don't worry, I'll give these values in a little bit. But we have Coulomb's constant, the charge of one object, the charge of the other, divided by the distance between them squared. Think of charge as the electrical equivalent of mass, right? It's an inherent property of matter. And charge, just like mass, is a conserved quantity. I can't just poof it into existence or destroy it. I have to be able to account for all the charge. So if I have opposite charges, a positive here, negative here, they're going to feel an attraction. And if I bring them closer, they're going to be a bigger attraction force, just like gravity. However, unlike gravity, it can also be a repulsive force. If I go for like charges, opposites attract, likes repel. So like charges or similar charges try and push away. They want to push away from each other. Similar charges do not like being close together. So let's look at a helium atom. A stable helium atom is two protons bound together with two neutrons. And I have to ask you, what force is holding them together? What's holding this thing together stably? So go ahead and pause, think of an answer for a bit, come right back. The vast majority of answers they'll often see, no one will, general, say B, only electricity. The electric force is driving these two protons far away from each other. Most often, I'll see people say that C. It's this combination of, hey, these neutrons are neutral, so gravity can dominate, and because of how close the gravity can take over and keep this glued together and overcome the electric force repulsion. But as it turns out, gravity is just not strong enough. When we're talking on these scales here, the scales of atoms, gravity is basically ignorable. Just doesn't factor in. There's going to be other fundamental forces for us to discuss. So let me build up the picture. Let me convince you that on this scale, gravity just doesn't matter. So let's compare the gravitational force with the electric force. So as a reminder, the gravitational force goes as the gravitational constant, 6.7, 10 to the minus 11th. This is newtons meter squared per kilogram squared. Reminder, Newton, that's the fundamental unit of force. If I was to push on you or drag and pull on you, I'm exerting a certain amount of newtons of force. The electric constant, Coulomb's constant, very similar thing, but this time it's 9.0, 10 to the 9th, newtons meter squared, Coulomb squared, right? Coulomb is the unit of charge, just like mass, kilograms, is the unit of mass. So yes, the electric force and gravitational force are incredibly similar. They're the basically identical equations. Only thing difference is mass is switched with charge, and our gravitational constant is switched with the Coulomb constant. And notice the orders of magnitude. There is 20 orders of magnitude difference between K and G. So let's put this into a calculation. Let's actually calculate electric versus gravitational forces. Now we're going to try and calculate gravitational force versus the electric force. I've got two protons here, and what I'm going to do is just separate them by 100 nanometers and say how strong is gravity attracting these things versus electricity repelling them. So, gravitational force, easy. Always attractive. Any sort of mass, gravity's trying to bring you together. So let's go into calculation. Gravitational force is gravitational constant, mass of proton, mass of the other proton, 100 nanometers, separating them, square that out, do things in the correct units, and you're going to find this value here. Right. What I want to emphasize, proton mass, that came from up here. We looked it up. Important number to have, and it is 1.6726 times, this is the important part, 10 to the minus 27th kilograms, right? That's our proton mass. Now let's switch over to the electric calculation. The electric force will be repulsive. We'll see the arrows trying to push these things away. Plug it in the formula. Coulomb's constant. Proton charge, same distance, 100 nanometers, square that up, and we'll get this result. Proton charge. This charge, or Q lowercase p in these slides. Go elsewhere, you're going to find people who call this E, others will call it Q, sometimes they'll call it capital Q. The most common form that I see people label this is a lowercase e. That's the most common one that I see in other books. But altogether, what matters here is that this charge of the proton, this 1.6022 10 to the minus 19th coulombs, this is a fundamental unit of charge. If you were going to be a cosmic being tweaking the size of the universe, if you're playing with what kind of universe you want to build and mold, this is one of your constants in the universe. Change this number slightly, and you'll literally change chemical reactions. You'll change the literal size of atoms, the structure of molecules. So I cannot emphasize enough how important it is, this fundamental unit of charge. A proton, all protons have 1.6022 times 10 to the minus 19th coulombs. It is a fundamental unit. All electrons will have negative 1.6022 times 10 minus 19th coulombs. I cannot stress this enough. So, with that stressing out of the way, now let's talk about the force comparison. Our gravitational force between these protons goes as 2 times 10 to the minus 50th newtons, while the electric force goes as 2 times 10 to the minus 14th newtons. So these are all SI units. They don't seem that big, minus 14th, minus 50th, but let's compare them. The electric force is about a trillion times stronger than gravity. These arrow here's grossly misrepresent the scale of discrepancy here. I want to say that the electric force is a trillion times bigger than gravity. So gravity cannot overcome the electric repulsion. When we talk about how strong gravity is compared to all the fundamental forces, gravity is basically ignorable on atomic scales. It just does not factor in. So, in our conclusion, how do you hold helium together? If electricity can't do it, gravity can't do it, what do you need? You need more fundamental forces of the universe. Here are our 4 fundamental forces of the universe. To the best of our current knowledge, these are all the forces necessary to build a universe that we see today. Gravity. This is the one that we first learn about. This is the one that we talk about the most, and it's also the one that we understand the least. We're not going to great details about why is the one we understand the least, but I just want that comment out there so that you're at least aware of this. Gravity is really great on the big scales. When you say have a star and planets in orbit around that, gravity tends to dominate. Essentially a fundamental reason why gravity matters on these big scales, where not so much on these atomic scales. Think about yourself right now. Are you electrically charged right now? No. Some of you might play that fun game where you kick your shoes off and then slide your socks on around on the carpet, and you'll build up a static charge. But you also very quickly discharge yourself. Walk over to a metallic object, zap yourself a little bit. On big scales, we tend to see objects achieving neutral charge, electrically neutral. Basically, you are composed of roughly an equal number of protons and an equal number of electrons. So over your entire body, you are net neutral, no net charge. Well, the same applies to the big objects. So on the big scales, the planets, they tend to be electrically neutral still. All right. They're about electrically neutral, and therefore the electric forces just don't dominate as much. Gravity is left to take over and hold the planets to the stars, hold satellites to their planets. Now we shrink down. We go down to the nuclear, the atomic scales. And these are where we're going to see things like electromagnetism matter. We've talked about the electric parts of it before. And you go back to section 5, you'll remember how we tied together electricity and magnetism as one force. And in principle, essentially, electromagnetism, this is what holds atoms together. If you want chemical reactions, if you want to have any complex molecules, it involves sharing of electrons. These different nuclei sharing their electrons to form nice stable atomic bonds. Now go smaller. Let's look at the actual nuclei themselves. Remember, every single proton in this nucleus has this strong repulsive force trying to push these things away. So there has to be something holding it together, and we call it the nuclear strong force. The force holding those protons and neutrons together in a nice stable nucleus, we literally call it a gluon that is being shared amongst all of those nuclei. There are gluons literally gluing the nucleus together. And yes, that is the conception of the name gluon. I'm not making this up. This isn't a bad joke, as much as we all wish it was, because it's a terrible pun. But it's literally a gluon carries the nuclear strong force throughout the nucleus, holding it together. Now, something has to be able to break that symmetry, so you can have things like radioactive decay. Somehow, we've already talked about how you can have a big complex nucleus, say like uranium or lead or even potassium, isotopes of potassium. Somehow that thing needs to be able to eject particles, spit out electrons, or spit out helium atoms or high energy photons. So what's the process? What's the force that allows for that radioactive decay? Well, that's the nuclear weak force. The weak force is what allows these things to spit particles, little bits of themselves outwards. So once again, as a recap, the four fundamental forces of the universe is gravity, electromagnetism, the nuclear strong force, and the nuclear weak force. And for the remainder of this section, we are going to focus on the strong force and how we get to fuse atoms together. This is going to be the powerhouse of the sun. I want to get our terminology clear, so I want to just formally define these. We're going to be talking about fusion versus fission. I'll start off with fission. Fission is you take a big, complex, heavy nuclei and you break it apart. Right? You spit out, let it decay into smaller materials. So fission is when you go from heavy nuclei breaking into smaller ones. This is what powers the nuclear power plants here on Earth. We're taking fissionable materials and exciting them, getting them to split apart, and using that to harvest energy out. Fusion. Fusion is when you take lighter nuclei, smash them together, and form a heavier, stable nuclei. That stable is a little caveat that we'll briefly encounter a little bit when we start to talk about the proton-proton chain. Fusion is the powerhouse of the sun. Fusion is how the sun is generating tons of energy that we get to absorb and consume today.